I'm Tim Ventura, and we're joined today by Roger Shawyer, a British chartered electrical engineer with 48 years' experience in the space and defense industries. Roger is the inventor of the EmDrive, and for the last 19 years has been the director of a small R&D company, Satellite Propulsion Research Limited. Roger's extensive career experience includes work at CAV Limited, Sperry Gyroscope, Marconi Space and Defense Systems, and more. Roger joins us today with an in-depth review of the highly publicized EmDrive propulsion technology, which has been featured in Popular Mechanics, Wired, Space.com, National Geographic, New Scientist, Forbes, and many other popular media venues.
Hello everybody. I shall be talking today about EmDrive, and I'll go through the theory, the engineering and the applications. Now the technical reports and the conference papers that are referred to throughout the talk, you can download from our website, emdrive.com. I'll take questions after the talk, but if you want to email me the questions, you can do so at the address shown. So what is EmDrive? Well, it's a new propulsion technology, which is a propellantless technology, not reactionless, but propellantless. It works by propagating a travelling electromagnetic wave inside a tapered section of waveguide, which is the cavity. It's resonant, so the wave travels backwards and forwards. At the large end of the cavity, it approaches the speed of light, and at the small end it's much less than 1/10 the speed of light. So the force at the big end is large and the force at the small end is small. Now this difference in forces causes a resultant force, which we call thrust, in one direction, which you can see shown by the arrow, and according to Newton's laws, of course, it provides an acceleration in the opposite direction. Now, one of the things that you'll hear about is that thrust can be very large for superconducting cavities. So where did EmDrive come from? Well, it goes right back to 1974 when Professor Eric Laithwaite suggested that gyroscopes could provide a means of reactionless propulsion. This was his 1974 Royal Institution lecture. Now, at the time, the UK nuclear warhead program called Cheveline was suffering from propulsion problems, and Sperry Gyroscope, the company I worked for, were under contract from UK MOD at Fort Halstead, Kent, on the Cheveline program, and in January 1975 were tasked to look at unconventional solutions to the propulsion problem. Well, I was part of the team that looked at this, and I went back to a paper by Professor Alex Cullen of UCL, a 1951 paper, and this was key to the solution that I proposed. It was an electromagnetic solution rather than the mechanical solution that everybody else was trying to do. I sent the report into Fort Halstead, and then in November of that year I was sent to Sperry headquarters at Long Island, and also down to their research site at Clearwater in Florida. And we discussed all sorts of microwave technologies, fairly advanced technologies. Then in October 1976, Professor Roger Jennison of the Kent University published the first of a series of papers on aspects of electromagnetic momentum, and he carried on through to 1989 publishing these papers. Meanwhile, I had gone back to my day job in both the defence and later in the space industries, And it really wasn't until the 1990s that the concept was resurrected, and it was run as a parallel program to Project Green Glow, which you've already heard about, and it became EmDrive. So let's get down to some basic theory. And first of all, we need to look at radiation pressure, which is the process which produces the force. Now, first of all, it is not pressure. If you look at the equation, F equals 2p over c, you can see that it is in fact a force, not a pressure. And Cullen showed that this equation can be derived from the basic electrical machine equation, F equals VLI, which all electrical engineers know, where B is the magnetic flux density, L is the conductor length, and I is the induced current. Now, this is the basic equation for all electrical machines. You can also derive the radiation pressure from combining Newton's F equals ma and Einstein's E equals mc squared. So the whole basis of EmDrive is classic physics, which has been around for hundreds of years. Now, Cullen also showed that the force on the end plate in a cavity is modified from 2p over c by multiplying by vg over c, where vg is the group velocity. Now, he showed this both mathematically and experimentally. And so in a tapered cavity, if you have two end plates with Vg1 at one end and Vg2 at the other end, then clearly the resultant force produced by the cavity is F1 minus F2, which is shown by that basic equation. Now, Dr. Bailey, who was actually a former pupil of Cullen, but was then working at the Royal Radar Establishment at Malvern, showed that this radiation pressure can be greatly increased by use of a resonant cavity. And this again he showed both experimentally and theoretically in 1955. So when you have a resonant cavity, you have a resonant frequency, and therefore you can change the thrust equation in terms of wavelengths. Lambda naught is the free space wavelength, and lambda g is the wavelength at the different velocities. And you can also then measure the resultant force from one transition of the electromagnetic wave to approximately Q times the transitions, where Q is defined as the stored energy in the cavity divided by the energy lost per cycle. So let me iterate that EmDrive is based on classic physics, which has been understood and accepted for many years. So EmDrive does not work like this. It is not the electromagnetic wave pushing against the end plate like a passenger pushing against the windscreen of a car. This is obviously wrong because any such force would be opposed by a reaction force R. And it stems from this wrong idea that photons are billiard balls bouncing off a wall. They are not. You have to treat them as electromagnetic waves, and you have to look at it a little more deeply than this rather naive construction. So EmDrive is an electrical machine. However, unlike a normal machine where the conductor is moving, in the case of EmDrive, it is the magnetic field that moves. So for the incident wave, the moving magnetic field H induces a current I in the direction of the E field, which you can see by the arrows in the diagram. Now this produces a force F, which opposes the movement M of the conductor relative to the field. standard electric motor idea. It's based on Lenz's law, which goes way back. And you can see that when the wave is reflected, the E field is in fact reversed. And this is similar to the back EMF, which is created in an electric motor. But the really important thing to take from this slide is that it is the conductor itself, which is the end plate, which pushes, rather than being pushed by the electromagnetic wave. And this was clearly put by a Chinese professor, Professor Yang Juan, who said that EmDrive is in fact a black box pushing against the rest of the world, just like us. So we now have to look at what happens in the cavity with this unbalance of forces at each end. And really the only way to solve this is to do a momentum balance. And there you start off with the wave being propagated in the middle of the cavity, where obviously at propagation the two wave momentums in the opposite directions must cancel out. Therefore rho1 plus rho2 equals 0. And if you look at the momentum at each end plate, you can see that the total momentum lost at the two end plates works out at 1.6 rho, and therefore the momentum gained by the waveguide itself must also be minus 1.6 rho. What we're just showing with this very simple balance is that EmDrive obeys conservation of momentum. One of the early objections to the EmDrive theory was that the sidewalls, the forces in the sidewalls would counteract the end wall forces. Now, and indeed this is true for just a standing wave, but you have to understand that the standing wave is a result of a large number of travelling waves. So if you look at the effect of the wave forces, you'll see that for surfaces which are at right angles to the wave motion, you will get a maximum force. But for surfaces that are parallel to the wave motion, you will get zero force. So clearly the idea is to correctly shape the cavity, and what's shown here are spherical end plates, such that the end plate forces are a maximum and the sidewall forces are zero. So we can look at this with a very simple mathematical model, and you'll see in the diagram we show both spherical end plates and flat end plates. Now for the flat end plate you will have an axial length of LA, but you'll have a slant length of LS. And if you look at what the path length error will be, the total path length error, then it is obviously LS minus LA. But for a resonant cavity, it will be Q times LS minus LA. And this very rapidly leads to a wavefront phase error, such that this phase error becomes indeed greater than half a wavelength very quickly. And this clearly will spread the bandwidth, reduce the Q, and will indeed introduce sidewall forces. You can see the what we call the mean path error effect on the flight thruster characteristic, where to obtain a Q of 55,000, which is what we obtained, you need to keep your mean path length error down to 0.1 of a millimeter. It requires pretty accurate machining, but what it does mean is that if you build a cavity with flat end plates, it really is a waste of time. You'll get zero thrust out of a flat end plate cavity. The other important law that EmDrive must comply with is the conservation of energy. And if you look at the diagram, you can see that microwave energy is inputted into the cavity. It is stored in the cavity for a short period of time. And if you allow the cavity to accelerate freely with continuous energy going in, some of the stored energy is then converted into the kinetic energy of the cavity. The rest of the input energy is continually lost as heat. Now, the important point about this illustration is that when the cavity accelerates, the stored energy will decrease because some of it is turned into kinetic energy, and therefore the thrust will decrease. And this is a lovely example of EmDrive obeying the law of conservation of energy. You don't get something out of it for nothing. Now, conservation of energy leads to a very interesting situation when there is no mechanical load on the thruster. If you look at the chart, you can see that in the first few microseconds after switch on, the stored energy, which is the blue line, increases according to an exponential function, whereas the kinetic energy increases according to a square function. So if the kinetic energy increases faster than stored energy, then I'm afraid the stored energy cannot build up, and the resulting thrust, which is shown as the green line, will just simply be a short pulse. Now this is important because when you're in orbit, where there is normally no mechanical load force present, you do need to adopt loading techniques to start up. Now, the inertial loading of the spacecraft itself occurs once the acceleration is established. So, if you only have inertial loading, you must also take into account what happens when the kinetic energy gained by the spacecraft becomes greater than the stored energy. And what you then need to do is to pulse this device. And so energy conservation is important because it dictates pulse operation when there is no other loading other than inertial loading. Now, for a typical simple first-generation thruster, these pulse lengths can be a few seconds, with the interpulse periods, as you can see from the graph, measured in microseconds. So effectively, you have almost a continuous thrust, but with just a small ripple. So now we get to a more complex part of the theory when we look at the effect of Einstein's special relativity. Remember that we have a cavity that has electromagnetic waves moving at relativistic velocities inside the cavity. So inside the cavity, Einstein's rules apply, whereas outside the cavity, Newton's rules apply. And the thing is that inside the cavity, the velocity of the electromagnetic wave is completely independent of the velocity of the cavity itself. So VG is totally dependent on the dimensions of the cavity and has nothing to do with the velocity of the cavity itself. Indeed, if you're an observer measuring the velocity of the wave, you'll measure it as Vg. You will not measure it as Vg plus Vc. This would take you above the speed of light, which is impossible. Now, to cope with this, what we do is we add a term S0 into the thrust equation, which actually is a term that uses Einstein's equation, the addition of relativistic velocities. The other point about this is that because the Vg is completely independent of Vc, the wave and the cavity form an open system. Also, although it's a closed cavity, as a system it is open and it allows momentum to be transferred between the wave and the cavity. However, during the acceleration of the cavity, you'll get a Doppler shift in the travelling electromagnetic wave. This is simply because at each end of the cavity the guide velocity is different. So you'll get a total Doppler shift in the travelling wave. This only really causes any problems when you have very high Q cavities, really when you're into superconducting cavities. But if you look at a simple mathematical model behind it, shown in the diagram on the left, you will find that you can calculate Doppler shifts for both an acceleration, a positive acceleration, and a negative acceleration, or a deceleration. So as you accelerate the cavity, you get a frequency decrease and hence an energy loss. So it acts, in fact, like an electric motor. If you use the cavity to provide a braking action, so you get a deceleration, it gives you a frequency increase and thus an energy increase, and the device is simply acting as a generator. So how does this affect a typical thruster? If you look at the characteristic on the far right, this is a superconducting cavity using liquid hydrogen cooling, and you can see as you accelerate, as the cavity acceleration increases along the horizontal axis, so an uncompensated thruster will lose its specific thrust fairly quickly. But there are methods of compensating, and this means that you can improve the characteristics such that you can get sort of reasonable accelerations of up to 1G is possible. Well, we've looked at the theory of EmDrive, and now we'll look at the challenges of the engineering of one of these devices. And as with all engineering projects, you start off with a design, and if you are going to correctly design the microwave cavity, you have to solve the guide wavelength and wave impedance equations. Well, these equations are well established. You can go to any microwave textbook. And what we've done is used a spreadsheet tool to solve these equations along the full axial length of the cavity using increments down to, say, 0.1 of a millimeter. And this has proved very successful for the last 20 years. We've predicted performances for different cavity shapes, sizes, using different modes. So, and each time we've got a very accurate prediction compared to the measured data. You can use a finite element software package to give you a picture of the E and H field structures, but you must remember that this is for a standing wave only, and it can give you an inaccurate picture when it's actually measured as a real cavity. This slide shows the design results for a TE113 CubeSat cavity. And you can see in the left-hand graph that the wavelength increases dramatically as you approach the small end at 140 millimeters, whereas the impedance drops off, heading rapidly towards zero. I mean, this is effectively demonstrating that the electromagnetic wave guide velocity is approaching zero as you approach the cutoff dimensions. If you look at the right-hand characteristic, you can see that we're able to plot both the E and the H field as phase plots. And this is important when you decide where you're going to place the input loop, which you can see in the blue dotted line is placed at a maximum H field. And where you're going to place the detector probe, which is an essential part of the cavity, where the red dotted line shows it's placed at an E field maximum. One of the most important processes that you must go through when creating a successful EmDrive cavity is to go through the tuning process that is necessary to ensure that the loaded Q that you actually measure comprises of the unloaded Q of the cavity and also the Q of the input circuit. And you can see from the equation that if the input Q is equal to the unloaded Q, then you will maximize the loaded Q. So it's important that the input circuit, whether it's a loop or a probe or a slot, must be tunable, and it must be tuned to match the cavity impedance at the input position and also at the resonant frequency F0. Now this causes quite a problem because the thermal response of the cavity and the input circuit are significantly different when you start putting real power into these cavities. And what this means is that the cavity tuning itself must be digitally controlled from feedback from a detector probe and the reflected power at the input. In practice, what you can do is you can vary the input frequency to cope with the variation of the impedances and the resonant frequencies of both the loop and the cavity. Now, when you're setting up a cavity, when you're doing the tuning, it is most important that you use the detector probe in a two-port measurement system. Many groups have tried to tune cavities by simply looking at the input power and return reflected power at a single port, the input, and what they do is they end up with a beautifully tuned loop. You know, it matches the 50 ohm source, both in frequency. It gives an apparent very large Q and indeed very large return losses. But what you're actually doing is you're simply tuning and setting up the loop with no coupling into the cavity itself. It's quite easy to do this, and it's deceptively easy, in fact. So if you're going to get power into the cavity as opposed to simply dissipating it in the loop, you need to use the detector in a two-port measurement system. And this is actually vitally important because many organisations have failed in their attempts to produce a thrust out of a microwave cavity because all they're doing is simply putting the power into the input loop. A good way of checking for this is to actually measure the temperatures across the cavity. And what you should do is you should see that the main thermal emission is at the large end plate. If you find that the temperature around the input connector shoots up, whereas the two end, well, particularly the large end plate, stays reasonably cool, you know you've got a problem, that you're not actually putting any input power into the cavity. So we have talked about the problem of the Doppler shift you get when you accelerate a high Q cavity. And in 2014, we worked out how to compensate for this in what we call our third generation cavity. Now, the basis of this is that the axial length of the cavity is slightly increased using piezoelectric elements as the acceleration causes the Doppler shift to reduce the actual resonant frequency of the cavity. Now, the one important aspect of this is that the waveform is now a circular polarization, and because, as any radar engineer will tell you, this enables you to easily detect the difference between the incident wave and the reflected wave, and this enables real-time control of the frequency and the axial length during each wave transition. Now, obviously, you can't keep extending the axial length of the cavity indefinitely, and this leads to the requirement for two cavities. And you can see on the right hand graph the effect of the increasing thrust in one cavity being counteracted by the decreasing thrust in the other cavity. These are exponential characteristics which follow the stored energy characteristics in each cavity, but the actual output is effectively a constant thrust with a small ripple. So now we'll turn to the development of EmDrive, again an essential part of any engineering project. And this took place in the UK from about 2001 through to, well, it continues to this day, but the bulk of it was done during 2001 to 2010. We were funded by the UK government and a bit of private investment. We were monitored technically by DSTL, that's the Defence Science and Technology Laboratory at Farnborough, where the main guy was a chap that some of you may have come across, David Fern. He was known as the father of UK electric propulsion. He's unfortunately passed away now, but he was a very good technical monitor. he insisted, for instance, that we were able to identify and calibrate out all the spurious forces that might affect the measurements we were making. We started in 2003 with the experimental thruster. This was a low Q, about 6,000, and we were getting about 19 millinewtons per kilowatt. It was driven by a standard commercial magnetron, which as you probably understand, is bolstered, so it's amplitude modulated. In 2006, we moved on to a demonstrator engine. Q was increased by about a factor of 10, so we were at this point getting 243 millinewtons per kilowatt. As a mean over many experimental programs with this particular engine. It was a complete engine. One of the things we did was actually to put it on to a rotating test rig, and videos of that are actually available on our website. This actually was the key to encouraging the American defence organisations to get interested into EmDrive. We moved on by effectively splitting our work between a flight thruster, which we finished in 2010. This technology was actually transferred to America under what's called a TAA, a Technical Assistance Agreement. This was all set up by the State Department and the UK Ministry of Defence. In parallel with the flight thruster, we worked on our very first superconducting thruster, an experimental thruster. Very difficult technology, but great fun to work with. Now, one of the things that I should mention is there is a big difference between the early two thrusters, which were using magnetrons, which tend to be fairly wide band, and therefore do not require such extreme manufacturing tolerances, but once you move to narrowband inputs from a signal generator and powered through as an amplifier, you need to move to very precise control over your dimensions and alignment. So here we have a couple of views of some of our test rigs. On the left you can see if you look very carefully, you can see the flight thruster set up on a static thrust measurement apparatus. This actually is a composite balance arrangement that's fully described in the test report available on our website now. Has finally been released for publication in the public domain. On the right you can see a demonstrator engine actually mounted on a dynamic test rig. This rotates on an air bearing. The whole rotating assembly weighs about 100 kilograms, and the idea was to demonstrate that EmDrive will indeed accelerate 100 kilogram spacecraft in orbit. If you look carefully at the videos, you'll see that the test rig rotates in an anti-clockwise direction, and in the photograph you can see you're looking actually at the large end plate, so it is accelerating in a direction large end plate to small end plate, and one of the beauties of this particular set of tests was it demonstrated absolutely that EmDrive obeys Newton's laws, and indeed the accelerations that we measured on the test rig, they were quite the same in terms of thrust as was measured on the static thrust measurement. So in effect, we were demonstrating F equals ma, which was very satisfying. So because EmDrive obeys Newton's laws, you must think about this when you're actually testing a thruster to measure thrust. And the thing you can't do is simply take an EmDrive thruster, put it on a set of scales, turn on the power and expect the weight to change. You know, that just is not going to happen, and it's fairly easy to see why. If you look at the left-hand diagram, you can see clearly that if the thruster doesn't move on the balance, then the thrust will be compensated by a reaction force, and of course you will measure no change in the balance reading. You will measure no weight change, and really you shouldn't. Now, one of the things about this setup is that you can use it to calibrate out all the noise on your measurement system. And this was a very powerful method of establishing what the spurious forces were, and what their causes were, and how we calibrated them out to satisfy our Ministry of Defence technical monitor. If you want to think about it as an analogy with a conventional rocket, it is simply like putting a conventional rocket engine on a balance, and again the thrust from the rocket, which conventionally points upwards, is compensated by the exhaust pressing down, if you like, on the balance pan itself, and again you'll see no weight change. All straightforward Newton's laws, but the thing to remember is that if the thruster is loaded with a mass which is greater than the thrust, you will simply not be able to measure thrust on a simple balance. So one of the things that has to be done if you're going to satisfy serious peer review or indeed technical monitoring is you have to be able to model mathematically whatever your test assembly is. And this is particularly important when you're trying to work with very low preloads on your thruster. If, for instance, you do a numerical model of this simple ideal beam balance, and then calculate what's going to happen over the first few microseconds after you switch on the thruster, you will see that, for instance, in the middle graph, that as you increase the preload from about 2 micrograms to 500 micrograms, the kinetic energy delivered to the thrust apparatus drops remarkably down, and this of course enables the stored energy to rise following a natural exponential curve. If you reduce the 500 microgram preload down to as low as 2 micrograms, then of course the kinetic energy shoots up, and in fact closely follows the stored energy characteristic. So there's only a tiny amount of thrust left, and you can see in the right hand graph for a 2 microgram preload, you get a very tiny, an almost unnoticeable pulse of thrust. And this is what happens if you don't add some preload to your thruster. And this is particularly important if you're going to test your thruster on a very high resolution balance arrangement. Ironically, the better the resolution of your test equipment, then the more of a problem you have with requiring a preload. So while we were doing our development work in the UK, there was work going on in China, Russia, and America. In 2006, a UK magazine called NewScientist published a cover page article actually on EmDrive, and this caused a bit of a controversy. In fact, a question was asked in our Houses of Parliament, and this little controversy caught the attention of some people in China, and at the Northwestern Polytechnical University in Xi'an, they decided they were going to start work on EmDrive. Now, this particular group have a lot of experience in developing and flying microwave ion engines. They were in fact brought into the Japanese Hayabusa mission when a problem arose on the return journey of this particular asteroid mission. So they know all about microwave cavities, and they quickly understood the physics and worked out the engineering. That they have some quite significantly effective test chambers over there, because they actually test flight thrusters, and in April 2010 they revealed they'd measured 720 millinewtons of thrust for a 2.5 kilowatt input. Now this actually is the highest published thrust to date. They published a peer-reviewed paper in 2012 and subsequently went on to do some other very interesting work. You should read their papers very, very carefully to understand the work that's going on in China. Now, in Russia, the first we heard about work there was in 2009. I was actually asked to comment on a report in Pravda that they had flown a perpetual motion machine in their Yubilini satellite. Now we looked very carefully at this and decided that if indeed it was an EmDrive thruster, it was probably operating around 8 gigahertz and was powered by what is effectively the standard X-band 40-watt tweeter. I've already mentioned that we caught the attention of the American defense business with our demonstrator thruster, and we attended a meeting in 2008, and this kicked off our long-standing association with America. And we did in fact complete a flight thruster contract with Boeing in July 2010. You can see in the slide, first of all, a picture of the Chinese experimental thruster. Interesting in that instead of a loop, here they use a waveguide slot input. And below the classic picture of our demonstrator thruster. So once we'd completed the initial experimental program in the UK, we carried on doing a lot of theoretical work and some additional experimental work. Tackled the problem of simply turning first generation thruster into a second generation one by using superconducting cavities. Now, there are a lot of problems with the IPCO substrate mounting. This is the so-called high temperature superconducting material we use, and I've mentioned the work we did solving the Doppler effect problem with accelerating the cavities. Now, along with the sort of this basic engineering work, we carried out quite a number of mission studies. Presented one at the IAC conference in Toronto, where we described a single-stage to orbit spaceplane and an interstellar probe. We wanted to show how wide-ranging the applications for EmDrive were. And they were, and they are, very wide-ranging. One of the commercial application studies we did was for the Shell company, and that was for marine applications. We introduced the concept of amplitude modulation to help overcome the Doppler shift problem. We kept a flight thruster back in the UK and loaned this to a couple of experimental groups, and we've given continuous support to a UK government research organisation. Interestingly, we were also granted an export license to export the technology to Israel, and basically we monitored as much as we could all the various efforts that were going on around the world, and now and again we helped out with theoretical understanding and tried to assist some of the groups to appreciate all the challenges that developing EmDrive produce. Now we've got to a stage now where patents have run out. Some of our NDAs have also expired, and therefore we can publish much more of our early work, including technical reports and descriptions of our design methods. Now, EmDrive did not go unnoticed by the press, and in particular, you can see three press reports identified on this slide, which claimed to be reports on in-orbit tests. I've already mentioned the Russian Pravda article, and this has been updated since with their Cosmos series of satellites. Cosmos 2499, I believe, was the last one that was reported on. In America, somebody, we believe it was a NASA employee, leaked the information about the X-37B spaceplane to IBT, that's the International Business Times, and that they did an article on this in November 2016, after carefully checking the sources, I understand. This was rapidly followed by a report in the China press later that year, and this was actually a press conference given by the Chinese Academy of Space Technology, where they claimed that they were flying EmDrive in their Tiangong 2 space station. Okay, so whether these reports of in-orbit tests are completely accurate or not, I don't know. My understanding is that the sources are quite reputable, and really I believe that we can expect a few more reports to be released into the public domain over the next few years. I mean, gradually the security blankets will be lifted from this technology because it will become more and more noticed. So we'll now turn to look at the results of some of our mission studies into the applications of EmDrive. We've done quite a lot of these over the years for all sorts of different clients, but we'll start with the first generation applications. These are for uncooled thrusters. Typical Qs are around 50,000 with specific thrusts around 0.3 of a Newton per kilowatt. And you can see here on the left is a 12U CubeSat, 50 millinewtons of thrust, operating for typically 5 years, would enable you to go to Mars or indeed fly out to Pluto. A very simple satellite of this nature with EmDrive propulsion simply opens up our backyard to all the science missions you want. If you look at GeoComSats, and these actually were the first commercial application we looked at, you take a typical ComSat, replace the primary and secondary propulsion with EmDrive, and you get rid of half the mass, because typically half the mass of these satellites is propellant. And of course, because you're no longer reliant on propellant for attitude and orbit control, you can roughly double the lifetime of any satellite, which should be attractive to the operators, if not to the actual manufacturers of satellites. So life gets a little more interesting when you look at the superconducting thrusters, and in this case we're looking at the second generation, which are straight liquid hydrogen cooled superconducting thrusters with no compensation for Doppler shift. So the accelerations are quite low, down to 0.05 of a meter per second squared, but we're getting pretty substantial specific thrust at typically 470 newtons per kilowatt. And just to illustrate the wide range of possibilities here, we move from, on the left, a very small UAV demonstrator, mass of about 60 kilograms, battery operated, short flight time, but very simple, and actually demonstrates that these things can fly. At the other extreme you have a 500,000 ton supertanker, and using complete closed loop cooling system, you can still improve the specific thrust of a tanker of this nature by about a factor of 3, as you can see from the figures that we quote here. So life gets even more exciting when you look at third generation applications. Now here we've used compensation for the Doppler shift problem, and we can accelerate up to typically 1G without losing too much specific thrust. We're running at specific thrust here of approaching 4 kilonewtons per kilowatt, very substantial. And if we look at the applications, on the left we see a personal air vehicle. Now because of the third generation compensation technique, we're now doubling up on the cavities, so we actually have an 8 cavity thrust frame, giving us the classic drone type control using four thrusters. Here we have takeoff mass approaching a ton, two-man air taxi type of vehicle. It only uses liquid hydrogen, so it's a green renewable fuel. And very importantly, this air taxi is a true air taxi. It enables you to actually fly from basically outside your house to anywhere else you want to go. You no longer have the problems that any prop-driven air taxi would have when you're flying in what are called urban canyons. Again, any helicopter pilot would tell you you do not fly into areas where the airflow from your downward props is going to be at all restricted. You tend to drop out of the sky if you do that. So a very usable personal air vehicle. The personal space vehicle on the right is absolutely fascinating. We were asked to see whether we could actually take 3 men to the moon and back again in a single vehicle, effectively doing what Apollo did. And yes, we came up with this vehicle, launch mass just over 10 tons. It doesn't accelerate very fast. It keeps it down to 0.01 of a G. Which does actually enable it to be used for the end market, which is aimed at space tourism. So we needed to produce a very gentle flight regime to the moon and back again, which actually will take of the order of 72 hours flight time. Absolutely fascinating mission study, and demonstrates the enormous advances that EmDrive give you in terms of transportation in space. One of the first applications that we looked at was in fact an unmanned vehicle. In this case, we wanted to look at how we would produce a heavy launch vehicle. And this now goes back to 2008 when we actually showed the aerodynamic test model of one of our early spaceplane concepts. Now, at the time, US Air Force Colonel Coyote Smith coined the expression that EmDrive is a space elevator without cables, and this essentially was what we were trying to aim for. The latest concept is effectively much as the original requirements were: 50 tons to geostationary orbit, fully usable 500 missions. Essentially, you simply hang the payload under the wing of this space plane, which indeed has obviously vertical takeoff and landing capability, but does have some glide capability. It's highly maneuverable. It's got pitch, roll, yaw, and also X, Y, and Z translation. So it can be used for docking and indeed for deploying payloads if necessary. It's obviously unmanned, fairly large wingspan, nearly 20 meters, total launch mass of 116 tons, of which 15 tons is liquid hydrogen. It again doesn't accelerate very quickly, 0.014 of a G, and takes something like 6 hours of continuous thrusting to get to geostationary orbit. The advantage, though, of this is that it's a very gentle flight envelope. Indeed, we restrict the maximum velocity through the atmosphere to 70 miles an hour. which means the mechanical and aerodynamic and thermal loads on the airframe are very low, and indeed it is really quite feasible for these vehicles to be manufactured by a truck company. You know, there's no real high technology needed in the airframe any longer. This is all a very gentle exercise, and the big thing, of course, is this brings the costs down dramatically, as we will see in the next application. And this application is probably the most important one for the world, and this is to be able to launch solar power satellites. These have been technically feasible for many years. Indeed, the seminal study report back in November 2011 says that there are no real technical barriers to this. The big barrier is to make them economically viable. And of that, the most critical challenge is at low cost, actually very low cost, Earth to orbit transport. If you take a typical SPS design, you need to get 6,700 tons into geostationary orbit to be able to generate constantly 2 gigawatts. Now, if you look at conventional transportation costs, you'd need 1,700 Atlas V rockets with a total cost of something like $194 billion, which is about $29,000 per kilogram. Now, the original study requirement reckoned you'd need to reduce this to $20 billion to make this particular solar power satellite viable. Now, we've obviously aimed to produce a very low cost transportation system using EmDrive, and we believe that we can bring the transportation cost for one 2 gigawatt solar power satellite down to $74 million. That is about $11 per kilogram. I mean, this is a huge reduction in cost, way below what the requirement is to make these things economically viable. And so effectively it makes solar power satellites the only real way to go for long-term energy provision for the world. The study we did showed that we'd need 134 launches, that we'd have to use airline type operation, you know, a 2-day turnaround. It'd take less than a year to build one SPS, and you'd also use the heavy launch vehicle that we described earlier to carry out all the docking and manoeuvring and indeed the deployment of various parts of the solar power satellite, mainly obviously the solar arrays. So we have a situation that EmDrive will be able to provide solutions to the renewable global energy requirement. That's quite a claim. Now, if you can get thousands of tons into geostationary orbit for solar power satellites, you can also get thousands of tons to the L1 point between the Sun and the Earth, and you can deploy orbital sunshades. Indeed, if you want to combine the SPS function and the sunshade function, you could do that, but you'd need laser power transmission to GEO and then microwave from GEO to Earth. The most important point about deploying orbital sunshades in this manner, apart from the fact that they can be done relatively cheaply, is that you have control over the actual amount of shade that you're putting on the Earth. In fact, you can have minute-by-minute control, because you simply change the attitude of these huge sunshades using EmDrive thrusters for the AOCS functions. So this is a completely controllable way of starting to shade the Earth, and this is necessary because we don't really know what's going to happen when we start shading the Earth, and you need to be able to do it step by step, understand the results of what you're doing, and be able to be in total control of shading. But the interesting point about it is that this would be, first of all, probably used for localized shading, and you can actually see the economic advantages of, for instance, a city deciding that they would actually like to have a lot more shade during the day to keep the inhabitants of this city a bit cooler. So you know, you can imagine cities actually funding their own sunshades. Now, if we're looking at global warming problems, you can also envisage international efforts to start shading the polar regions so that we stop melting the icebergs. So what we have is that EmDrive can enable solutions to probably the most important problem of our age, which is global climate change. This I think is a very important aspect of the future of EmDrive.